let's chat a little bit more about least squares. I'm going to have this be a little bit more interactive today as well. We'll do some things in Python. Have you do some things on Python. Work a little bit with it. But before we do that, let's review how we found our model. And then we're going to talk about a method of how we might evaluate how good the model is. And we'll do some computations in Python. Okay? All right. So remember last time, the idea was to try to solve the matrix equation AX equals B when A is an m by n matrix with m being greater than n. Solving a system of solve a system of linear equations written in matrix form. So I'm just writing it a little bit more succinctly, right? This is just another way to write a system of linear equations. And it's overdetermined. Remember, overdetermined means that we have more equations than variables we're solving for, right? So the idea behind this is maybe you're collecting data and you expect the data to fall along some pattern, whether that pattern is a linear pattern or a quadratic pattern or what have you. You expect it to fall along that relationship, but due to measurement error or precisions of your instrument or what have you, there's error in the data. There's error, and it's not going to fall directly on that curve, whether it be a line or a quadratic or what have you, right? So our goal here is to try to get it to fit as well as we can, right? And that's what we refer to as that least squares solution, right? So again, the picture was I've got some representation of the column space of A. Again, I know many of you haven't heard the terms. All we mean by column space is that treat each of your columns like it's a vector and do all the possible linear combinations. That's all column space means. Okay? All right. So the idea here is, of course, I've got an overdetermined system. What that means is that our vectors are living in, say, R5, but maybe I only have 3 columns. So I can only possibly generate 3 out of the 5 dimensions. Okay? And then maybe I've got another vector that doesn't fall into those 3 dimensions. So we've got some other vector, we'll refer to it as B, that doesn't lie in the column space. And that's what makes the system inconsistent. Okay? So again, try to think about it in terms of things that you know. And probably the easiest example I'll draw on the board is just thinking about it in 3-dimensional space. Okay? If I'm going to generate all of 3-dimensional space, then I probably need at least 3 vectors. Right? If, say, I only have 2 vectors, then I can get a plane, but I can't get everything, right? So as a simple example, if I have a vector pointing along the x-axis, say I, and a vector pointing along the y-axis, say j, I can't get anything that's off the xy plane. Does that make sense? Okay, so that's the idea behind this. All right, so I've got more equations than variables. So if I set it up as a matrix, I'm going to have longer columns, or I'm going to have longer columns than I have rows that are wide. Because I've got more rows than columns. So if I think of each as a column vector, I've got my vectors are living in a higher space, then I have a number of vectors going across my columns. So I can't possibly generate all of the space that it lives in. Okay, that's the idea. So when we're trying to find this least squares solution, well, I know that anything down here is some AX. And really what I'm trying to solve instead is this projection of the B vector into the column space of A. I'm going to take that shadow of my vector B. I'm going to force that shadow to be in the column space, to be a linear combination of the columns of A, and then solve that system instead. Okay? That's the idea behind all of this. So really down here, I really have just this projection that's down here, and I'm not going to bother putting the little subscript in the projection there. Okay. So this vector that I've drawn down here is the projection, and I want to figure out what linear combinations of the columns give me that projection. That's the picture. Okay. Remember again, we refer to this as orthogonal projections. We want that to be perpendicular. Geometrically, it makes sense that that is the shortest way to get there, right? Just looking at it from a triangle standpoint. If I tried to go, put this in red so it looks a little bit different. If I tried to go anywhere else, that distance is going to be longer than that one because I got a hypotenuse of a right triangle, right? And so that's where the name least squares comes from. The distance is the shortest if I drop it perpendicularly, if we do the projection. And distance has something to do with sums of squares. So that's why it's least squares. That's where the name comes from. Okay. We talked last time, well, I have this system, and I'll leave it like it was to start with. We have this system. It's not square. Square systems are a little bit easier for us to solve because if I have a square system, I might be able to multiply by the inverse and be able to solve it, right? So to turn this into a square system, what do we do to both sides? Multiply by something. What do we multiply by? The transpose of A, right? We took A transpose A, X equals A transpose B. And we gave this a name. What name did we give this? Those are the normal equations. Good. Pardon me. Good news is that these normal equations are always going to give us some sort of a least square solution. It may not be what we want, but it'll give us some sort of a least square solution. Okay. We hope it's unique. It doesn't have to be. You can get multiple least square solutions. We won't have cases where we don't have non-unique ones, but it can happen. Okay. So you can have multiple least squares, and all that means is that in some sense, there's multiple different ways to represent that projection as a linear combination of the columns of A. And basically, you just have more columns that you need. You have more columns that you need to give you unique information. I know many of you have already talked about spanning sets. Just because something spans doesn't mean it spans uniquely. So if you have non-linearly independent columns, then you could have multiple least square solutions. We're not going to worry about that. I'm just telling you that it can happen. Okay. All right. So, pardon me. We hope this is, we have a square matrix here that we can invert. Because if we have a square matrix that we can invert, then we can just find our least square solution by doing the inverse of that matrix on the left-hand side. This is what we refer to as a least squares solution. And then if we really want to know what that projection vector is, if we really want to know what the projection of B onto the column space of A is, we just hit it with the A. We've solved it. So the projection is A times A transpose A inverse times A transpose times B. That gives us the projection vector that we want. Okay. All right. So we did this last time. We solved one of these. We'll do another one here. I'm actually going to let you solve one of these here in a little bit. But before we do that, one of the things that we want to talk about is how good is this approximation? Okay. All right. So going back to our original set of equations. Oops, what the heck happened? Going back to our original set of equations here, remember that we were trying to solve this AX equals B equation, right? Now, again, we probably don't get this solved exactly because it's overdetermined, right? That was the whole point, okay? So really what I can think of is our B here is something in the column space plus some error vector. Okay. So and again, if we're doing a least squares solution, we want the magnitude of that vector to be as small as possible. That's the whole idea of the least squares part, right? So if we go back up, again, we're thinking about this as squares. If I go back up to my picture, I'm going to erase this red bit that's in here. Here is my A times my X. Here is my B. This would be some sort of representation of that error vector. It's perpendicular to it, right? Now, in terms of data, we have measurements that go, we're going to change this into a linear algebra problem again. But in terms of data, we have something that's referred to as the total sum of squares. And all of this has to do with error. So I think about collecting a bunch of data. When you're doing a total sum of squares, you're looking at how far the data is from the mean of all of it. That's what the total sum of squares is. In a linear algebra perspective, if you think about vectors, it's the magnitude of each of your data points minus the mean squared. Remember I'll write this off to the side just so you remember. Remember that the magnitude of a vector x, well, let me call it I'll call it v, is the square root of the sum of the squares of the components. That's how we do magnitude. Now, when you did calculus, did you like taking derivatives of square roots and then having things on the inside? No. So that's why we square it. It just makes the computations easier. Okay. If I minimize the square of it, I've minimized the square root. Square root is an increasing function, right? So if I minimize the inside, then I've minimized the square root. It doesn't change anything. So I might as well just square it and not worry about it. Okay. All right. So that's why I worry about the total sum of squares here. It looks like this. So if you were to write it out longhand, it would be the sum of I equals 1 to n of y sub I minus y bar squared. Okay? That's what that looks like from a vector perspective, right? If I subtract two vectors, I subtract their components. But the component of that y bar vector, if I think about it as a vector, is just the mean is every single entry in the vector. I subtract the first data point from the mean, I subtract the second data point from the mean, and so on down the line. Okay. All right. So from a linear algebra perspective, we can actually write this nicely, which seems kind of strange. So let me write down a matrix that's going to look weird, but then we're going to see why the weirdness helps us out here. Okay. So I'm going to define this matrix N. This matrix N is going to be the identity matrix. It's going to be the N by N identity matrix. And then minus 1 over N times, I'm going to write it as an I and an I transpose. I didn't put a dot above my I because that's supposed to represent the Greek letter iota. It's nothing fancy. Okay. Here's what I is. It's just a vector full of ones. Sometimes this is called the indicator vector. And it's written as the number 1 in boldface, but I can't write in boldface on my paper very easily, even though I'm not writing on paper. Okay. I can't write in boldface very easily, so that's why I've got the little vector notation about it. This I is literally just a vector full of ones. I'm sorry, this iota is a vector full of ones. We have to be fancy in math. We have to use Greek letters. Yes. Yes. Yep, it's just one column. So let's talk a little bit about what iota times iota transpose is. Okay. What dimensions does iota have? The way I have it written. You told me it was just one column, so it must be something by 1. It'd be an n by 1, right? If I'm going to get things to match up. So then iota transpose is 1 by n. So when I multiply the two things together, I get n by n, right? So I'm going to get an n by n matrix, which is better if I'm going to subtract it from the identity, right? Okay. Let's see how that works. It's not very interesting because it's super not interesting. It's just a fancy way to write this. All right, so I've got a vector full of ones this way, and I've got a vector full of ones this way, and I'm going to get an n by n matrix over here when I'm done. Well, remember how you do matrix multiplication. You line up row with column. How many multiplications do I have to do? No, just for that one. How many multiplications? You just have to do one multiplication, right? Row 1 has 1 entry in the first matrix. Column 1 has 1 entry in the second matrix. So what's the product going to be? 1. Now go to the next one. Row 1, column 2 multiplied together gives me a 1. Row 1 times column 3 gives me a 1. I'm going to get a bunch of 1s, right? So this iota times iota transpose is just a fancy way to write a matrix of all ones. Super interesting. It's a trick to help us do computations. Okay. That's what we're getting at. All right. Before we go on to that, you remember dot product for two vectors? What's another name for dot product? So what's the fancy word for dot in dot product? Those of you who had me for linear know the word. Starts with an I. Okay, I'll tell you. It's inner product. That's the word we use, is inner product. It's the fancy word for dot product. The reason why we use a fancier word is because not all inner products look like a dot product of two vectors. Some of them, if you have functions that are your vectors, they could be integrals, right? There's other ways to describe dot products, but we use inner product. One way to write inner product of two vectors is take the transpose of one times the other in that order. Transpose of the first times the second. Okay, so if I think of them as columns, the first one would be 1 by n, and then n by 1 gives me a 1 by 1 matrix, or might as well just be a scalar, right? This order is reversed, so instead of an inner product, what type of product do you think that's called? Outer. It is. It's called an outer product, yeah. It's the outer product of those two matrices. Okay. So this would be the outer product of I with itself. The reason I mention it is because NumPy has an outer product operation. And outer products have other applications. Our application is to help us do that sum here in a second. Okay. All right. So let's think about what this matrix looks like. What does the identity matrix look like? Yeah, the diagonals got ones and zeros everywhere else, right? What does that second matrix now look like? When we did iota times iota transpose, we got a matrix full of ones. So what does 1 over n times that look like? Yeah, they're all 1 over n's. Yeah, so I got a matrix full of 1 over n's here. That's some bad handwriting, but that's just a bunch of 1 over n's in there. And now subtract it. Well, the only place that you're really doing any subtraction of any consequence is on the diagonal, right? So your diagonal is going to look like 1 minus 1 over n all the way down. Every other entry is going to be a negative 1 over n. Whew, that was a long way to get to that. What's the point? You should be asking yourself that, because I've just said a lot of words that don't seem to be connected to anything that we're doing. Right? Agree? I said like this sounds like a lot of words that I haven't done anything with, right? All right, so what's the point? Here's the point. If I do n times y, or times b, I mean, I might call it y every once in a while because one of the books I was reading with this stuff, it has y's instead of b's. All right, so I got 1 minus 1 over n here, minus 1 over n, minus 1 over n, minus 1 over n. A lot of writing. All right, let's call it B1, B2 out to Bn. All right, so let's just look at the individual entries here. I'll write it out longhand to start with. I've got an n by n matrix times an n by 1 vector, so I should end up with an n by 1 vector. But let's see what we get. Let's ignore this 1 for the time being. If I just had a bunch of negative 1 over n's all the way across times that b1 out to bn, what would I end up with? Think about it another way. Don't even think about them as 1 over n's. Think about it as ones. If I had 1, 1, 1, 1 all the way down, and I multiplied it by the b's, what would I end up with? Close. Say it again? One more time, sorry. Just end up with the B's. You know, it just end up with the B's, and what are you going to do with all the B's? Add them, right? Because remember, we go row times column, we have to add every entry, right? So it's 1 times B1 plus 1 times B2 plus all the way down. Okay, so now if I change it from 1s to 1 over n's, it's going to be 1 over n times the sum of the b's. What's another name for I add everything up and divide it by how many there are? It's the average, or the mean, right? So when I take the negative 1 over n's times everything down, I'm going to get the mean. And I'm subtracting it. What's the 1 here give me? It just gives me that first entry, doesn't it? So when I multiply this out, I'm going to have B1 minus, I'll write it as 1 over n times the sum of the B sub i's. What's the next row going to be? Well, it's going to be different in the second row from the first row. It'd be B2, right? Because the 1 has moved over to the second spot, right? So this will be B2 minus the B's all the way down. Now it looks like I've taken each of my B's and subtracted the mean, right? So if I take the magnitude of that, I get that. If I take the magnitude of this vector, I get this. Just with B's instead of Y's, right? We agree with that? All right, so one way to take the magnitude of that vector is multiply the transpose of the vector times the vector. We just said that a minute ago, okay? So that's the square of the magnitude. So the square of, I'll write it as B, the vector of B minus, I'll write it as B bar. Remember again, this is a vector with all B bar on it. Just writing it that way. If I want to be really, really hyper-technical, I could put that little iota on it so that I have the same entry all the way down. Squared will be NB transpose times NB. Okay? How do you do a product of a transpose? What would you like the transpose to do with respect to the product? What would you like anything to do with respect to a product? It doesn't always work, but what would you like anything to do with respect to a product? Oh my goodness. What do I do with the A here? Distribute, good. I'd love the transpose to distribute, right? The each factor. Does it do that exactly? It does in some sense, but not exactly. What do you have to do with the order of the factors? Think about it in terms of matrices. If I want to multiply an m by something times a p, what has to be true about these two dimensions? They have to be the same. If you transpose them, would your product work in that order? No. Does it work in the reverse order? Yes. Okay. Some of you had me for linear. I know you know this. Yeah. By the way, it works the same for inverses, right? The inverse of a product is the product of the inverses in the reverse order as well. Okay. All right. Let's concentrate what's on the inside here, because we can actually simplify this a little bit. Okay. Remember how n was defined a minute ago, right? N was defined as I minus 1 over n I transpose. Let's take the transpose of that. With respect to sums, what can we do with the transpose? Same word. Distribute. Thank you. And this time I don't have to worry about order. Distributes to both pieces, right? Well, the first piece is the identity matrix. Identity has ones down the diagonal and zeros everywhere else. If I flip it along the diagonal, does it look any different? No. So I still get I there. That's a constant times a matrix. Does that constant affect the transpose at all? You can multiply by the constant and then take the transpose, or I could take the transpose and multiply by the constant and get the same answer, right? So I can pull the constant out. And we just said a minute ago that the transpose of a product is the product of the transpose, but in the reverse order, right? So I'd have I transpose transpose times I transpose. And I'm saying I because iota has way too many syllables for 4 letters. Okay. What happens when you take a transpose and then do the transpose again? Get back to where you started, right? Does that look familiar? That's where we started, isn't it? So N transpose is itself. All right, so that's one simplification we can do. By the way, a matrix that's its own transpose is called what type of matrix? Ooh, I think I heard it. Oh, well, it is square. It has to be square to start with, but it also starts with an S. Yep, it's symmetric. Yep. Matrix has its own transpose is a symmetric matrix. Anytime you take a matrix, that A transpose A matrix, for example, will always be symmetric. Okay. All right. Let's see what else happens, because there's another simplification we can do. Let's see what happens if we take n times n. I'm an algebraist. I could do this stuff all day. This stuff, I like this stuff. All right. I want to multiply those two things together. This you've done since Algebra 1. What do you think we need to do? Yeah, it's FOIL it. Exactly. Oh, we're going to FOIL. Right. Cool. All right. I times I. If I take the identity times itself, what do I get? The identity, right? The whole point of being the identity, right? If I multiply by anything, it doesn't change it. Okay? So that helps with the other two, right? I'll have a 1 over n I transpose minus a 1 over n I transpose, and that's just the identity times each of them, right? That's the outer and the inner. We agree? Yeah. Okay. Oh my goodness. Now we've got minus 1 over n squared I transpose I transpose. And order matters when you multiply matrices, right? I can't just start flip-flopping things around. Order matters, but I can regroup however I like. Matrix multiplication is associative. Okay? That helps here because here's how I'm going to group it. Let's think about what that answer is. That's I transpose times I. That's an inner product. That's a dot product, right? How is I defined? What were the entries of I? Ones, right? So I got a bunch of ones. Then I'm going to line it with a bunch of ones and take the dot product. What am I going to get when I take a bunch of ones dotted with a bunch of ones? What number am I going to get? How do you take a dot product again? multiply each entry, and what do you do with all of those products? Add them, right? So if I take a bunch of ones and dot with a bunch of ones, what number am I going to get? If I take n ones and dot with n ones, what number am I going to get? N, because I'm adding 1 to itself n times, right? So that entry there, or not entry, that product there is just going to be an n, and now it's a scalar, essentially. It'll cancel with this, right? Oh, by the way, I do have a sign error. It's a minus times a minus is a plus here. At least that's fixable quickly. This is the same thing as this is the same thing as that now, right? I end up with I minus 1 over n I transpose. And what's another name for that matrix? N, yeah. So we get this relationship that this matrix n, when I square it, I get back to where I started. That property is called being idempotent. Just to write it down. If you take a power of a matrix and end up getting, or power of something and end up getting 0, it's called nilpotent. The ID is for identity and it stayed the same. I took a power, potent, and then it stayed the same, identical. That's where the word comes from. Nilpotent would mean it goes to 0 eventually when you take powers. Okay, those are 2 words that pop up in algebra. All right, whatever. You don't care about that. Let's go back to where we were. Okay. N times n here I can now replace with just an n. All right. Phew. Okay. This is a matrix way to represent, this is a matrix way to represent that total sum of squares. Okay? And squared error, if you will, in some sense. Okay? All right. Why do we care? I don't know. Why do we care? Let's go back to where we were. Remember again, we had that b equals ax plus error, right? That was where we were, right? Hit it with an n. Well, think about it this way, by the way, before we get there. This is our data, if you will. This is the part of the data that's explained by the model, whatever that model happens to be. This is what's left over. Noise, if you will. Okay? This is the explained part, this is the unexplained part. Okay? So this is your regression part, this is your error part, if you will. Okay? All right. Let's hit both sides with n. That doesn't look very interesting. Okay. But hit it with an n because we're going to use this n matrix again to give us that sum of squared error idea, right? Now, I'm not going to go through it because it requires a little bit of technical things. This, when I take the n times the e vector, as long as your model has a constant term, and that was the technical part that I'm going to gloss over and not talk about, as long as your model has a constant term, that n times e will always come back to e again. It doesn't change the e vector at all. All right. So we wanted total sum of squares, trying to explain the error, right? That's the idea here. Okay. So to do that, again, notice we said we could get that total sum of squares by doing this computation, right? We agree? Okay. So if I want n b transpose times nb, this right-hand side will just be this times its itself without a transpose. The left-hand side was B transpose NB, right? That was the left-hand side. Let's see what we get when we distribute out the right-hand side. Well, first I got to do the transpose before I can do any distribution stuff, right? Okay. So distribute the transpose through, that will reverse the order here, right? So I'm going to write this as X transpose A transpose N transpose plus E transpose. That's just distributing the transpose to each term in the sum and then distributing it over the product. Right? Now let's FOIL it, but let's not write every single detail out. When I take the first times the first, I'm going to have an N transpose hits that N, right? But what did we say N transpose was equal to? N, and then N times N was N, right? So that first term just becomes X transpose A transpose N AX. Right? We agree with that? Okay. So the next parts I'm going to come back to. Right? The last parts are going to be E transpose times E. It's going to turn out that those two inner terms actually give you 0 for both of them. And let's talk about why. Okay? Let's talk about why that's 0. All right, so let's go this vector times that vector. Okay? All right, so we have X transpose A transpose, pardon me, and then N transpose times E. So just doing the outer terms multiplied by each other. What did we say that N transpose was equal to? N. And then NE was equal to E, right? So at this point, we've got X transpose A transpose times E. Right? Do we agree with that? Okay, cool. All right. Remember now, though, that this X was really our least squares solution, right? That's what we're thinking of this as being the least squares solution. How did we find the X? Well, it was that whole big mess, right? It was A transpose A inverse times A transpose times B, right? In any event, how do I want to do that? Trying to save a little bit of time. So your X really is A transpose A inverse times A transpose times the B, right? The transpose of that would be everything in the reverse order, right? So it'll be B transpose A I feel like something's out of order here. A transpose A inverse. Something's out of order. I'm not going to spend the time on it. Trust me when I tell you that the inner terms go away. Let's just go with that, okay? Something is out of order when I multiply through by what I need, the things will cancel out. You could, I'll put something together and send it out. This is not worth a ton of time to figure out what I've got wrong there. In any event, you can think about why the piece in the middle has to go away. Remember again that we're doing this projection idea. The projection idea gives us a Pythagorean theorem, right? If I'm doing these things with sums of squares, that's just a squared, b squared, c squared here, right? The piece in the middle should go away. Okay. All right. In any event, just to give this a quick little name, remember these were the projections, right? The AX was the projection once you find your least squares solution, right? Okay. So just to call it consistent with the B's, I'm going to write this as B hat and transpose, B hat, and then E transpose E. Okay. So this is your total sum of squares, which a lot of times is abbreviated SST. This is the part of the error that's explained by the regression, the linear regression or least squares, right? Okay. So a lot of times you'll see this called SSR. This is regression sum of squares. Total sum of squares, yeah. And this part over here is SSE, or your error sum of squares. Now, depending on what book you look at, including the book that I was looking at to put this stuff together for lecture today, they reverse SSE and SSR. They say SSE stands for explained sum of squares, and then residual sum of squares. This part is actually called the residual, by the way, which is why you get flip-flop names sometimes. Doesn't matter because I'm not worried about that part. That's the part that we can't explain. That's the part that's going to be there regardless of how good your model is. Okay? That's the noise, if you will. All right? So a measure for how good this is what's referred to as the R squared value for your model, and that is SSR over SST. That's a measure of how good your model is. And so it's just this formula. It will be your B hat transpose NB over B transpose NB. It's your predictions squared in some sense. It's the square of the deviations of the predictions divided by the square of the deviations from your data. That's R squared. Okay, so let's go into Python and see if we can do that. All right, so let's just create some data for us. All right. Oops. So let's import NumPy. Let's import import the linear algebra package as well, so we can so that we can use the linear algebra commands like norm and solve and those kinds of things. Okay. All right. So let's create a scenario here. All right. So let's generate 500 random x values between -3 and 3. So the command for not random, I'm sorry, equally spaced x values between -3 and 3. That's not random. it will equally space 500 points throughout that interval. That's what lin space does. Okay. The random part here is that I want to see some sort of a quadratic fit here, but have some noise introduced. So let's say we do, make one up here. Let's do, say, 1.75 x squared minus, let's say, 3 times x. Let's do a plus, let's do a plus like a 1.2. And then let's add some random noise in here. All right, so at the end of this thing, I'm adding some random noise. So this is just, if I didn't add the random noise, I would literally have a bunch of points that fall directly on a quadratic. Okay, so what we're doing is just tweaking the y values a little bit. This is doing a random a certain number of random points from a normal distribution. The normal distribution that I chose to use had mean 0 and standard deviation 1. That's what the first two entries are. And then the last entry is how many points you're going to draw. Okay. Oh, I forgot to import something else because I don't want this. Sorry. Let me also import matplot lib.pyplot as PLT. All right. We should be able to get a scatter plot of this and see what we've got. Oops, x, y. And show the plot. If you're typing this in along with me, you should have a similar but slightly different picture once it actually decides to load. There it is. There's a scatter plot. The points are kind of big. If you want to make the points a little bit smaller, one of the, I think it's just points. Is it points or is it point? Well, I'll find out here in a second. Yeah. Okay, is it just P? Well, let me see. I've got this in another file. Marker. That's what the word is, not point. Sorry. There it is. I can make the points a little bit smaller by just putting that extra attribute in there. I've been using R as well for a class I'm taking through the U of I, so R uses point. Anyway, there's a scatter plot. All right, so let's remember how we get our model. We want to fill a quadratic model here. Pardon me. Fill a quadratic model here. So we need a column full of ones, a column full of the x values, and a column full of the x squared values that we have, right? So we can get a column full of ones by doing the np.ones command and tell it how many ones we want. We've got 500 points, so I better have 500 ones. Right? Okay. Then to create our matrix A, we can do that column stack command. Column stack takes a list of numpy arrays to create your matrix. So one of them is going to be 1, one of them will be your x's, and one will be your x squareds. Right? And now we can actually solve our system in a couple of ways. One way we did it last time was to do literally type in the LA dot inverse of A transpose A times A transpose times B, or in this case times the Y's. You can also use the solve command under linear algebra. Remember, we could also solve the normal equations, right? Remember, your normal equations are A transpose A, X equals A transpose B, right? That's our normal equation, right? So if we use the solve command rather than doing the inverse, we could type in A transpose times A. That's the coefficient matrix. Remember, we do dot capital T to get the transpose. We use the at symbol to denote matrix multiplication, right? Then comma, and then we'll do A dot transpose times the y's, because we're using y's here, right? I did x's and y's rather than called it B, right? That gives us our coefficient. Yeah. Okay. We can declare our polynomial. I'll call it P. That was np dot polynomial of the coefficients. By the way, there's actually two ways to create polynomials from a list of coefficients in NumPy. One's use that polynomial. The other way is to do polynomial 1D. That requires them to be in decreasing order for the degrees. That flips it around. I have no idea why. Okay. All right. So that gives us our polynomial. Let's generate our y, or I'll call it y hat, with p of the x's. That's our predicted y's, right? They agree? That's the predicted y's. That'd be our b hat, if you will. Okay. And let's do our plots again. So let's do our scatter plot. And let's do our plot of x's and the y hats. And I'll change the color to red so that we can see it a little bit better, hopefully. And hopefully I've got everything typed in here correctly. All right, so again, this is just we already have our x's formed, right? We did that with that linspace command earlier. We're getting all our predictions based on the y's. The pyplot command of plot plots all those dots in place, connect the dots, and we have so many of them that it'll look curved rather than a bunch of sticks. Okay. And there it is. You should have something that looks similar. It should not look exactly the same. Because again, you should have used a different random sample than me. So your points should be slightly different. Not horribly different, but slightly different. No, we've already passed that. I can't possibly do that. Is that what you need? Okay. Okay. We okay with that part? Okay. So let's see if we can figure out what the r squared value is. I have my y's. I have my original y's. I now have my y hats. I just need to define that n matrix, right? So that I can do my top and bottom of my r squared, my SSR over SST, right? Okay. So let's define a function that you might want to use in the future. So I don't have to retype it every single time. np.identity creates the n by n identity matrix in NumPy. There are two ways that you can do this next part, and it really doesn't matter which way you do it because it's equivalent. One way is to do np.outer, because that was the outer product that I told you before. All right. And I want to do the outer product of the vector of n1s and then comma the vector of n1s with itself. So that's one way to do it. Remember, we took the vector of 1s and the vector of 1s and did the outer product. That's one way to do it. Okay, so that's what np.outer will do. We'll take the outer product of those two vectors. Another way to do it is, I'll just write it on the board so I don't have to retype it. You can do np.1s. You can do n squared of them. But that will just give you one long n squared vector of 1s. So you use the reshape command, and that'll make it an n by n matrix of 1s. That's another way to do it. Both of those work. Literally does not matter which one you use. And if you want to play with it, you can check that they both work. There's probably other ways to do it too, but that's two ways that you can do it. Okay. Actually, I'm 100% certain there are other ways that you can do it. Okay. All right, so there's my n matrix. We want the r squared value, right? So I'm going to define n to be our n matrix with 500 points. Guess how many points we had, right? Was 500? We want SSR over SST. SSR is our y hat transpose times n times y hat. And our SST is the y transpose times n times y. Okay. And I should get a number if I've typed in everything correctly. Should get a high number. The closer to 1 that is, the better the model explains what's going on. Because there's an explained part and an unexplained part, right? We want the explained part to be high. We want that ratio to be high. So the closer to 1 that ratio is, the better. 0.98 is a really good R squared value. It basically says that 98% of the error in the data is explained by the model. And then we have a little bit of noise left over. Is that okay? That's literally what you would need to do for the homework. That's all. That's what we have in there for the homework. Okay, part of that. There's other little pieces of it. You use the model to do other things, but that's how we figure out what the R squared is. Also on Moodle, and I didn't get a chance to do it since we've got 4 minutes, and I'm not going to try to do it now. On Moodle, I posted a little bit of code. It's actually in a text file. This text file will download a data set, and I've got it to where it's going to pull out horsepower versus miles per gallon, trying to predict the horsepower from miles per gallon. Play with that data set a little bit, see if you can come up with a model that looks like it fits it pretty well. Try with a linear model, try with a quadratic model. And then on Tuesday, we'll talk about another way we might try to find a different model that actually relates to kind of what you do by asking you to do in the third problem on the homework. Okay? So play around with that data a little bit, see what you come up with. And otherwise, we will see you next time. Have a good one. I feel like I've exhausted you with some linear algebra.